6th of January Leetcode challenge. Today's question is Kth Missing Positive Number. In this question, you are given an array of positive integers that are strictly sorted in nature and also an integer k. You need to tell the kth positive missing number that is there in from that array. Let's walk through an example here so that we get hold of the concept. The question says you are given 2, 3, 4, 7, 11. This is the input array, and you need to tell the fifth missing positive number. So if you write all the positive numbers starting from 1 till infinity, and you will check what are the numbers that are missing from this input array, then the fifth number in line would be 1, 2, 3, 4 and 5. Hence 9 number becomes the fifth missing number that is absent in this array. Had it been the first one, it would have been 1. Had it been the second one, it would have been 5th. Had it been the third one, it would have been 6th, and so on. Also, it is given to us that the length of the number is up to 1000, k lies from 1 to 1000, and so on. Also, it's also given that the numbers are in increasing order. They're sorted in nature. So let's walk through the algorithm, the slideshow that I have created here, and kth missing positive number. And let's talk about the naive approach. The naive approach states that let's create a set of all the numbers that are there in this array. So I created a set. The set contains 2, 3, 4, 7, 11, and it's given to us that k equals to 5. Let's start the iteration from the value 1, and we'll keep on moving in the loop till we don't find the kth missing number. How are we going to do that? If you find the iterating element in the set, simply just increment the iterating element. If you don't find the iterating element in your set, reduce k, because that counts for one missing entry, and increment the iterating element to the next pointer. So let's walk through this logic. It's given, let's start with 1. 1 is missing, so we reduced it to 4, and we incremented 1 to 2. 2 is present, we incremented it to 3. 3 is present, we incremented it to 4. 4 is present, we incremented it to 5. 5 is missing, 5 is not there, we reduced k. K is gone. Then we get 6. 6 is missing, we again reduced k. K becomes 2. 7 is there, let's move ahead. 8 is missing, we reduced this to 1. And 9, we incremented this to 9. 9 is not there, it becomes 0, and we get our answer. So pretty simple, a naive approach. What will be the space complexity of this algorithm? The space complexity of this algorithm will be the number of elements present in this input array. So if 1000 elements are there, the complexity is order of length of the number of elements present in this array, order of length of array, length, I would say. And the time complexity would be linear, because you are moving for order of k, because you are moving from the start to finding the kth element. So let's walk through an optimized approach, which is better in both space and time complexities. Let's talk about binary search. I hope you are familiar with basic concept of binary search. You calculate the mid element. The binary search operates on the sorted array. You calculate the mid element, you take 2 pointers, low and high. You find out the middle element. If the middle element is equal to your element that you are interested in searching, that is the index. Otherwise you move, if it is less, then you move to the lower pointer to the higher value, mid plus 1. Otherwise you reduce the higher value, the higher index, by mid minus 1, the standard way. In this example, you are given an array that contains 1, 2, 4, 5, 6, 7, 8, 9. And let's calculate the middle element. The middle element is the total number of elements are 8, and the middle element is equal to 0 plus 8 by 2, that is 4. So the 6 is the middle element. And how many numbers are there that would have been there in the array starting from 0 till mid. So there were 5 elements in totality, mid plus 1. And if we calculate the difference between these two, the total number of elements that would have been there and the middle element, that is 6 minus 5, that is 1. And this gives us a count of the number of missing elements from the input array. Had it been the case, this element would have been 5 here. There would have been no element missing because repetition is not allowed and the elements are sorted. So the difference between these two values gives us the number of missing elements, and the missing element is 3 as in this case. Hence this statement is correct. Let's walk through another example. Here we have multiple elements missing, 4 and 5. So what is the middle element? The middle element is 7. 7 minus the number of elements that would have been there up to the middle position is 5. So 7 minus 5 is 2. So again, difference gives you the count of missing elements. Let's walk through the other example. Here in this case, the middle element is 10. 10 minus 4 plus 1, that is 5. 10 minus 5 is 5 again, and the missing elements are 4, 5 and 7, 8, 9. So the equation, array of mid minus mid plus 1, the number of elements that should have been there, it gives us the number of missing elements. And let's apply this algorithm to binary search. What are we going to do? If the number of missing elements is greater or equal to k, if the number of missing elements are greater or equal to k, we reduce our right pointer and we'll move towards the left index, because this is there are more missing elements in our input array, in the input subset that we have chosen. Similarly, if the number of elements that we calculated is less than k, that means the answer lies somewhere on the right side of it, and we'll increment the left value to mid plus 1. Standard way of writing the binary search approach. Exactly, I have restated it here. Let's calculate the number of missing elements at each index. If the missing number of elements is greater than equal to k, we move towards left because we are too much on the right side, and hence high turns out to be equal to mid. If we are too much on the left side, that means the number of missing elements are less, then we move towards right, left becomes equal to mid plus 1. Let's quickly code it up. 0 and integer high, that is equal to the length of the array, and till the time low is less than high, we don't breach this condition. Let's calculate the middle point. Midpoint equals to high minus low by 2 plus low. Standard way of writing, so as to avoid overflow condition, although it is not possible in this case because we are given the limits, upper and the lower bound, but still it's a good practice to write it this way. If array of mid minus mid plus 1, that means we are calculating the number of missing elements. If it is greater than equal to k, that means we are too much on the right side of the array, we need to move towards left. High equals to mid, otherwise we will move towards the left side of the we'll move towards the right side of the array. Low equals to mid plus 1. Return low plus k. So using this binary search, we have found out the first index, the smallest index to which adding k will give us the answer. That is the starting position to which from which up to k elements plus k elements will give us the position of the missing element, then the value of the missing element. If it passed, let me just submit it. Accepted. Let's talk about the time complexity of the approach. Time complexity is of standard time of binary search log n, and space complexity is order of 1, constant time. Thanks for watching the video. Hope you enjoyed it.